basic. And what we're gonna do is what I did at some conferences, I'll probably be doing in Atlantic City a year from now. And what we wanna do is take certain geometry concepts and formulas and see where do they come from. You know, why is the area of a parallelogram not length times width? Why is it base times height? Why is a trapezoid the way it is? Why? Because the book says so? Well, you know, what kind of a stupid answer is that? We want to see where it comes from. Why are the formulas the way they are? You okay, Scott?
Yep, there you go.
All right, so let's see how it's showing up. It's showing up upside down, of course, so we'll have to go this way. Zoom in. Because we need to get a little bit bigger so they can, we may be okay with this. See if you can get it bigger. Bigger. That's gonna be good. All right, at any rate, I've done a couple seminars. I just want you to see how to spell my name. It's Silski, and I'm from Waynesburg University. If you ever want to call me, or if you'd like to go to Waynesburg, I'd be more than happy to talk to you. But what we're gonna look at today, guys, is, you know, where do some of these formulas come from that Mr. Van Sickle taught you? So let's start really basic, all right? Even though I'm not the best artist, what is this thing? A rectangle, right? If this is 6, then this is? Okay. I teach college geometry, which is basically what you guys do on steroids, kind of. We do a lot of the high school concepts, but then we apply them. How do you find the volume of a steel beam? We actually did this one. What is the volume of Noah's Ark, honest to God? We did that problem. Biblical scholars know how big it is. We did that. You know, how much cement do I need to do whatever I need to do? But here's where a lot of people kind of get confused. So we're gonna start basic and work our way up. By the way, I'm gonna call on people, Scott.
Yep. Just call it.
Yeah, I don't know anybody's name. So the perimeter, this is where we better be careful. The perimeter of this guy with glasses, how would you find the perimeter of that figure?
Need all the sides.
Go ahead.
32.
32. Now I haven't told you what that is, what they are, even though it isn't. Let's pretend it's in inches. So the perimeter is 32, we'll say inches, right? Good. Inches. Could have been feet, could have been meters, could have been inches. 32 inches here, guy with the glasses. One of the things I've been doing for all the years I've been teaching is if you get the right answer, you get a reward. But I used to tell people, Scott, if you get the wrong answer, you get side kicked in the head. And now that I got artificial,
Yeah, you
I can't side kick anymore. Area's a little different. Area's a little different, isn't it? So, one of the things people don't realize, area is not in inches. What is it in? Inches squared to square inches. If I can do this, why is that? Well, think about it. Now, of course, these aren't 1 inch, but we're going to pretend they are. If we were tiling a floor, oh, that's a little too big, maybe a desktop, and we were putting down tile, think about it. If I actually started counting, which I'm not going to do, how many of them are there altogether?
60.
Right. Who said 60? The guy in the glasses again. You're on the ball now. I'm not giving you another treat though. At 60, you guys said in inches squared. If we were dealing with a fish tank, volume would be inches cubed. Good. So what I want to do today, guys, is let's start with the most basic figure, and we're going to use the document camera for most of this. And what we want to do is, where do these formulas in geometry actually come from? That's what we're going to look at today. So let's remember our rectangle. And I'll bet you guys know, because Mr. Van Sickle taught you, do you remember the formula for the area of a triangle? Area of a triangle, have they done that?
Yeah.
Area of a triangle, do you remember the guy with the curly hair?
It's half on the base times height.
Yeah, very good. 1/2 times the base times height. You get a Waynesburg pen. You didn't get any bubble gum, sorry. Hey, it's free, right? Why? So let's take a look at some of these things. So Scott, I guess I gotta stand on this side of it, huh?
Yeah.
Unless we turn it around. Would that work? I bet that would. I bet I'm not as dumb as I look. Let's try. Let's see if this will work. I bet it will. Look, well, yeah, this is either way, I'm gonna have to write this. So guys, let's talk about where that comes from. Let me get that set. No, we're okay. So let's take our rectangle, right? We already said the area of a rectangle is length times width or base times height. But think about what I'm going to do to the rectangle. I could cut the rectangle in half many ways. I could slice it that way, I could slice it that way. But I've chosen to cut the rectangle in 2 parts by slicing it diagonal. So what I'm telling you, and you guys probably know this, we've cut the rectangle into 2 equal parts, right? I can certainly prove it. We're going to be doing a lot of cutting today. Because like I said, everything in geometry, most of the stuff we do is derived from other formulas. So I'll cut my rectangle out. Oops, let's get it correct. And as we said, the area of the rectangle, everything moves backwards, is base times height. Where's width as or length times width. The guy in curly hair said triangles 1/2 base times height, and we can prove again where that comes from. Conservation of area. I'll cut it right along the red line. And as you can see, if we superimpose them, if the rectangle is base times height, and I put one on top of the other, the triangle is 1/2 base times height. You can see, what if it's not a right triangle? We can still prove that, believe it or not. But that's where 1/2 base times height comes from. But I'm actually not done with the triangles yet. I'm really not done with the triangles. So, let's take one of the triangles, let's take this one. And let me ask you guys another question, you can pitch this. Do you guys remember, this is a tough one. Do you remember what the angles of a triangle add up to? How many degrees? This guy's already answered. How many degrees did the angles add up to? Do you remember? And you would be right. Scott, you're a good teacher, man.
Yeah, Darren got lucky.
You're the best. This is Darren.
Yeah.
Here you go, Darren.
Thank you.
You got your pink shirt on?
Yeah.
You know my wife is a breast cancer survivor?
Really?
Yes, indeed. 5 years now.
That's
God bless her.
Dr. Cross's son there.
Really, that guy.
Yeah, unfortunately.
You ask your dad. If Dr. Sealski, I used to play basketball with him for years, he and I played together. Ask him at the end of the game, with 10 seconds left, who he wants taking the last shot. And you see what he says. Okay? He might tell you anybody but him, but I want you to ask him that question.
I will.
I know you will. So we're going to do something here. Because Krauss told us that all all the angles of a triangle, added up to 180 degrees. And since he's Krause's kid, I have some serious doubts if that's true or not. So what we want to do is to see, indeed, is that the case? Do all the angles of a triangle add up to 180? Well, I'll tell you what I did. I took all the angles of the triangle and I cut them out. And I'm going to piece them back together like a jigsaw puzzle. Give me this Scotch tape. Somebody stole it. Oh, gee whiz. And as you can see, if I cut all the angles out and do it just right and get this thing on the way it should be, I've cut all the angles out. What does it form? A straight line. And if you remember, a straight line from one end to the other, 180 degrees. By the way, it'll work with any triangle. Did you ever see that before? Cut all the angles out, piece them together like a jigsaw puzzle, it equals 180 degrees. You just proved it. You just proved it in geometry class. And I could have done any triangle. I just happened to use the one. I may use another one in the next class. Here's a souvenir to give to your dad. By the way, your dad was a very good defensive player. I'll say that. I always hated playing against him. I used to have to kind of like elbow him a little bit.
Well, he's down a little bit lower on everyone.
Okay, guys. Do you remember, by any chance, let's take this figure, our parallelogram, and a lot of students, guys, think, let's take this called the base or the length. We'll call this the width, and we'll call this one the height. So, there's our parallelogram, and I'm sorry that the end got cut off. I apologize for that. Let me get it a little bit over more. It's tough to move on this thing.
Yeah.
We'll do the best we can. So the parallelogram, a lot of people think, okay, if the rectangle is length times width, why isn't the parallelogram? Why don't I just multiply base times width, length times width? Doesn't that work? No, it doesn't. Won't work. Say, no, why not? That's what we're going to look at. Why isn't the parallelogram this side times this side, like many people think? Well, let's take a look at why not. So again, let's do a little cutting. Conservation of area. I'm not going to change the figure as far as its total area. I'm just going to cut this side, this triangle right here. I'm going to take this triangle. Remember, I'm not changing the total area of the figure at all. I'm just going to take that and I'm going to transplant it. I'm a surgeon here. I'm going to transplant it right there. So what did I do? I physically took, hey Scott, can you make that, let me see if I need to make the thing a little bigger or not. You can't make that bigger, can you? You make it bigger so the whole thing comes on. The other way. More. Beautiful. So what did we do? We took the triangle, we transposed it from here to here. What figure do we have left, guys? What is that thing? Rectangle, right? And the rectangle we said is length times width, or, as you learned, base times height. Base times height. So, there you go. Why is a parallelogram not length times width? Because if you actually cut and paste, you can transform the parallelogram into a rectangle. And now, obviously, look, this is still the base from here to here. If this is the height, this is also the height. So we can actually cut and make our parallelogram into a rectangle. Everything we're doing today, guys, for the most part, is gonna go back to the basic figures. Does that make sense? Did you ever wonder about that? Why is the formula the way it is? There's a reason for everything, guys. I'm probably gonna need the board again in a minute or two. Scott, keep me appraised of the time. I don't wanna run out of time. I got a lot of neat stuff I wanna do. Here's one. This one may be a little, let's see. Scott, have you guys done a trapezoid?
Yeah,
Oh,
before.
you did? You actually did the trapezoid? Okay, let me do something here real quick. If you guys will give me a minute. Let's take, let me make sure I get it centered. Let's take our trapezoid. There it is. Do you remember the formula for the area of a trapezoid? Because that's a tough one. Ooh, now I gotta go, area of a trapezoid, do you remember what it was? It's a tough one, man. Area of a trapezoid, if you don't remember, I'm gonna write it down. And then I'm gonna show where it comes from. Area of trapezoid, let me help you out here. 1/2 times the height times what? Very good, base 1 plus base 2. Well, why in the heck is that? Where in God's name does that come from? I was hoping you did double figures.
No, it's always not.
Really? My dad used to sneeze and it sounded like it was like a nuclear explosion. Let's see where this comes from, gang. So what I'm gonna do is I'm gonna take my trapezoid and I'm gonna cut it into 2 triangles. I'm gonna take the red triangle and we're going to take the green triangle. Because remember, we already know, you and I talked about this a few moments ago. We talked about the area of a triangle, we even derived it. It's 1/2 times the base times the height. So, we got, it's kind of tough for you guys to see the red and green, isn't it? Maybe you can kind of tell, the bottom triangle here, let me go up and point to this thing. So I cut the trapezoid into 2 triangles, right? This is, even though it's hard to see, here's the red triangle, here's the green triangle, you with me? So, here we go. H, right? Maybe I ought to go write it in. Doing a lot of running here today, so.
In the end shape.
No, I'm gonna go work out for about an hour when I'm done here. I have a gym in my basement, seriously. I got everything, I got a couple karate bags, I got a bike, a stair climber, a elliptical machine. Got everything. So guys, let's take this triangle, all right? Let's take that triangle, and let's take the area of that triangle right there. The red triangle. The area of the red triangle. 1/2 times the base. What are we using for the base? B1, right? 1/2 times the base times the height. You with me? You agree?
Yeah.
1/2 times the base times the height. The area of the green triangle. 1/2 times the base times the height, which is still h. Well, the entire trapezoid is the sum of those two things, right? Sure it is. Everybody had algebra, right? What's the common factor here? What's the common factor between that and that? 1/2 h. I'm gonna take it out, right? Remember common factors? I'm gonna take out the 1/2 h. What's left here? V1, right? What's left here? How about that? Now I could cut the triangles out with the scissors, but there's no reason. There's where the formula for any trapezoid comes from. Because any trapezoid can be cut into two triangles. So if you ever wondered where it came from, there it was. Now you may have seen those before, but I guarantee you, you've never seen what I'm going to do next. Because even my college geometry students never did. And I would like to take credit for the next thing I'm going to do, but I can't. Because it was done by a Hindu mathematician sometime in the 16th or 17th century, believe it or not. Here, Scott. You know what? Let me just put this aside. Use it again. Scott, do all your students know the Pythagorean theorem?
Yes.
You do. Everybody knows the Pythagorean theorem? You think, right? The Pythagorean theorem says for any right triangle, guys. Okay, let's go draw one up here. You got all these black. You don't need any other colors besides black, huh?
Nope, that's all we got.
That's all right. Well, let's take the Pythagorean theorem. You guys all remember this, right? For any right triangle. Here, let's hear it. Come on, all together. A squared
Equals B squared.
equals,
C squared.
okay. But we're gonna take what we've learned, so pretend we've done nothing else but what we did today. We're gonna take the concepts we learned today. We're gonna prove that. Only using what we know about a triangle. What's the area of a triangle?
180.
What's the area of a triangle? Triangle, 1/2 base times. What's the area of a rectangle or a square?
This one side,
I didn't hear you.
one side times one side.
Yeah, right, one side times one side, very good. You got a good class, Scott. So we're gonna take that knowledge and see if we can't prove only using the area of a triangle and the area of a square, which we already know, right? We proved it in class. We're gonna see if we can't prove Pythagorean theorem. So what we're gonna need to do here is again put together a little puzzle. So here I'm gonna try to get this together so that you can see it. I'm gonna take that triangle. Scott, zoom in a little bit. I want you to zoom in more on this one. And I'll tell you when to quit. Good stop. Yeah, I may have to move it over. Okay. Here's a triangle. A, B, you'll see it as I put some other ones. A, I know it's upside down. B, C, right? Here's a right angle. A, B, C. That's A, that's B, that's C. And we already know the formula for the area of a triangle, right? It's 1/2 times the base times the height. You with me? It's 1/2. The area of this triangle, we'll call this the base, even though it's not marked, there's a little B there, A, B, C. The area of that triangle is 1/2 times the base. But I could call this the base, it doesn't matter. 1/2 times the base times the height. So 1/2 times the base times the height. That's for that one triangle, right? There it is. There it is. I'm going to put another of the same exact triangle, ABC. And I'm going to put another of the exact same triangle. Gotta get it right though. A, B, C, these are all the same size, take my word for it. And I'm gonna take another of the exact same triangle. So, how many triangles do I have now? 4, right? Does that make sense to everybody? 4 of these, an exact same triangle. So the total area is how many of these? How many do you see up there? That's right. Now, let's use a little cleverness. There's a missing piece. There's a missing piece. It's a square. We gotta figure out how long it is. How long is that side there? Remember, this is B. Gotta figure this out. How long is that side from there to there? Remember, C, A, B. Remember, this side's C, this is A, this is B. So it's kind of listed for you, from there to there, how long is that side? B, right? You with me? It's B. C, A, B. That's B. How long is it from here to here? A, right? From there to there, say it again, from there to there. B, from there to there. B, A. So each side of the square is B minus, you with me? There, this is B, say it again, this is B, that's A. So do you see that each side of the square is B minus A? Does that make sense? I'm going to put the last piece of the puzzle. I have it written down, but I want you guys to come up with it yourself. So let's put the last, and that'll complete the entire figure. So, what did we say it was? It's a square, and the area of a square, according to that guy there, was each side square. How long is that side?
C.
C. See, the area of the whole square is C squared, right? That's a no-brainer. Okay. So let's see what happens when we do some algebra, huh? Why don't we do that? Four times 1/2 times B times A.
2BA.
Thank you, 2BA or 2AB. Now, Scott, does everybody in here know how to square the binomial?
And sure, they normally split it out.
B minus A, remember that B minus A times B minus A? Remember how to do that? Remember FOIL? Help me out. B squared minus
BA.
BA minus BA, A times A, A squared. You with me?
Yeah.
Do you remember that from algebra? So here's the area of the 4 triangles. That's the area of the little square, right? The area of the 4 triangles plus the area of the little square should equal the area of the whole thing. Well, go to that expression. What cancels out?
2AB.
2AB. What do you have left? There you go. You proved it. You didn't have to take the book's word for it. You proved it yourself using nothing more than the fact that you knew the area of a square and the area of a triangle, which we also proved. So we started out with the area of a square, rectangle, Scott, and we proved everything using that, everything. Triangle, parallelogram, trapezoid. It's a beautiful thing, Scott. How much time do I have left?
You have, I'd say, 12 minutes.
We can probably do what we want to do then. So you got me a nice round object, right?
Yep.
Thanks, Scott. You're a good guy.
Sometimes.
despite what people say.
That's a-
I would like to know, and I'm gonna throw this out to the audience. The 11, how many are in here? 2, 3, 4, 5. Hey, like you said, there were 11 people in here.
Absent.
Somebody's absent.
Yeah, Lucy's not here.
Oh, gosh, Lucy's not here. What is pi? And do not tell me 3.14. I don't want to hear that. Let me use a bad word. I don't want to hear that stuff. I don't want to hear 3.14. That is just, that's an approximation. I want to know what pi is. And you know what, Scott? My college of geometry students, most of them can't tell me this. Where does it come from? Don't tell me the bakery. Where does pi come from? Nobody knows, do they? I'm going to show you where it comes from. So, I may need your help, Scott. So get off your you know what and help me out. So guys, I'll tell you what I'm going to do. I'm going to take my thread here. And with the help of Mr. Van Sickle, we're going to talk about what pi is. So, here, hold your finger on that. We're going to measure all the way around the can. This maybe, hopefully we can do this. We'll get that lid out of there. Okay, what we need to do is wrap the string all the way around the can.
Need some more string.
Oh, well, then we'll get some. Okay, we need to get it pretty exact. You hold that down there, and I'm gonna get it right to there. Okay. Right where my finger is. All right, let it go. So, we measured the distance all the way around. You're not done yet,
I'm
Scott.
getting you scissors, I figured you
Uh,
might need them.
Yeah, I'm probably gonna need them. Right, cut it right there, dude. You're a smart guy, Scott.
Sometimes.
So what did we just measure the distance around the can? What's that called? Do you remember? Circumference, right. So Scott, your job is to measure, I'm gonna hold this out, let's measure the circumference with my ruler that I brought in. Get one of your students to help you hold the string and you measure it.
Laura.
Get Laura to help. I want you guys to measure that string in inches. The circumference of the can. And we're going to do this in every class and see which one wins. And remember, we're just approximating.
Say 15 inches.
I want it really, really exact. Is it exactly 15, pretty
That's
much?
about as close as we will get.
Yeah, I mean, if it's not 14 and 7/8, is it? I want to get real exact if we can. If it's 15, that's fine.
It is 14 and a half. That's-
Really?
Yeah.
Okay, so let's call it 14.5. Now, guys, this one will be a little easier, Scott. We can use the same string, and again, I'll need your help. This one's gonna be a little tougher. We need to measure from there, hold that right at the end, and we're gonna measure the distance. You know what, I bet it's easier on this side. When a couple of rocket scientists we are. Hold that down there, right on the end. And then we'll measure the distance across right to there. Okay?
David, answer.
That's about 5. It was a little more, it's about 5 and 7/8.
Thank you. The way you can see.
5 and 7/8 is that. So, what is pi? Well, why we did that is where pi comes from. And nobody knows this, but you're gonna figure it out. All pi is, guys, and this is in any circle, it's the distance around the circle divided by the diameter. So Good, help me out, Scott. You get it out your calculator.
Velocity.
We're gonna go again.
She's just a noise maker.
It's all right. Scott, I want you to take 14.5 divided by 5.875.
2.468.
Now, we didn't come too close. We're supposed to get 3.14. Now, we're gonna do it again in the next two classes. The closest I ever came at Waynesburg Central, I got 3.12. That was really close. But we used a bigger object, we used a garbage can.
Okay.
The bigger the object, the better it is. I bet you guys don't know this. This is a secular school, but I don't really care. In the Bible, they actually list pi in the Bible. And this, I guess it was the Greeks or the Romans, they got around 3, which was pretty close back then. I forget what book it's in, Leviticus or something. It's actually in the Bible. You know who told me that? Dr. Bush. So now, if you guys, well, hopefully you learned a lot today. If somebody says, what is pi? And by the way, pi is unitless, because inches divided by inches cancels out. So you can tell your friends, your relatives, all pi is the circumference of any circle divided by the diameter. Does it matter how big it is, guys? No. We have something big, we don't have a
I'll try to
garbage
find
can.
something bigger.
Yeah, find a big garbage can. We used to have a TV show in Waynesburg called Math TV, and we did a show, it aired on Channel 14. We did a show called What is Pi? So everything we did today, guys, what did we start with? Just a rectangle, square, and every formula we did was derived from that. So guys, I appreciate your letting me come and talk to you today. I hope you learned something. You probably won't have any homework today because, see, that's, and some of you even want some treats. So guys, thanks for your attention.